Okay, so last time we talked about the vector, how to implement vector in amortized time, and we talked about mostly about amortized time generally. And then we started to talk about binary search tree and how to implement their insertion, deletion, and contains in external and internal binary search trees. Okay, today we will continue talking about binary search trees. So we will be talking about binary search trees in general. Then we will be talking about AVL on balanced trees. We will talk about AVL, and then we will talk about Treap. Okay. Hello. Okay, good. Okay, let me probably reduce my voice a little bit because it's too loud. So, what we talked about previously, we had BST and we have insert, remove, and contains. Now suppose we are asked to do two additional operations. We have additional operation next and pref. So that given the binary search tree, it will give us the next element after this or any other position. So next x and pref x tells you the next element that is at least higher than x, or like the pref is less than x, the closest element. So how do you think we can implement next? So again, remember that in binary search tree we have a tree such that in the left all their keys on the left are less than the key in this node, and everything on the right contains keys bigger than this one.
Yes, we can just go to the right to take the next element, I guess.
Okay, okay, so suppose we have like some node that is somewhere going like up here, and then so this node, okay, and we want to find the next one. What are you going to do?
I think it would be the right child of it.
No, the next one, not the right child itself. Because like suppose that let me fill all their sorry, 1, 2, 3, 4, 5, 6. The guy on the right is not necessarily to be the next because he's bigger than everything on the left. Okay.
Okay, so it would be the leftmost child of the right child.
Okay, that's already a good guess. That's a good guess. So like we should go to the right once and then go always to the left until we find the node here. Okay, that's one thing. But there is an issue is that if there are no, so we want this element and there are no right child here, who will be the next?
Maybe it would be up. His parent would be.
For example, here the parent is on left.
Yes.
So it's a little bit more complicated. A little bit, like not.
The parent would be less than.
Yeah, the parent. Like this depends, right? It can be like that, or it can be like that. So sometimes the parent is the next. If this guy has no right neighbors, then this should be the next.
So maybe we should go in the left case. Maybe we should go to the parent and then to its parent. Well,
Like, can you tell me what? Yeah, what in general? Okay. So when we go up to the left, who will be the next?
The next of our
Like suppose like this is the parent to the right, so kind of this guy is the left. Who will be the next?
So his parent should be the next.
Yeah, this should be the next.
Yes.
Okay, that's good. Then suppose this left guy is still here, is going to the left, like kind of this is the right child, so we can say that this is the next, but it is the left child of someone. Then who is the next?
This one.
Yeah, this guy. So can you probably decide an algorithm on that?
Yeah. Well, in this case, we should follow the left nodes until there is right node.
Yeah, exactly. So like this is exactly the same case. So we kind of go to all the left. There is nobody on the left. So we go to the right, and here the next. So it's just the same situation. You just go up by the like right pointers, and then go to the right. So like I guess you will understand how to do pref. Like pref is kind of the same, but you have to revert the situation in general. So that's how like there are two options, right? Either there is a guy on the right. If there is a guy on the right, then we go to the left until we find an element. Please note that like we should stop if, for example, this guy has right child but doesn't have left child. We should stop here because this is the leftmost guy in the subtree. Otherwise, if there are no right child, then we should go back and go to the parent, and some of the parent will be the next. Okay? I think this is quite reasonable. Like if you have questions, please ask. I'm looking at the chat. So okay. So this is typically what BST is about. But what is the problem about BST? The problem is that, like in the average BST, is that let us think that we have, for example, I don't know, internal binary search tree, okay? And you add elements one by one. What elements, like, is it possible to get like this? Like 1, 2, 3, 4, and etc.
Well,
can we get a tree like this?
If we add them in sequence.
Yeah, if you add them one by one, you will get exactly this tree. But this is not what we really want, right? Because like this is slow. You will like the height of the tree is m, which is a lot bigger than one should expect. So typically for that, there is a balanced binary search tree on how to balance the tree to make their height logarithmic. So why logarithmic? Because if you consider their most perfect balanced tree, it is their binary search tree with full of nodes, and if you have n elements, then its height is logarithm n. Okay, so we are targeting so that the height of each tree, like the height of tree at any time, will be logarithmic. So let us start from a little bit more complex tree than we will talk later. The tree that we will talk later. we will be talking about AVL tree. So it is the tree because it is named Adelson-Belsky, so it's Russian tree. That's a short amount of Russian, how to say, like Russian data structure that there is. Like there is a method of 4 Russians, but as I remember, they're not Russians, they're Chinese, and there were only 2 of them. But the method itself is named for Russians, like, and this thing is like it's Russian balanced binary search tree. So what is the idea behind that? Let's maintain the following invariant: that for each node, the height of the left subtree and the height of the right, like let it be HL. So this is L, this is R, and the height of R. We will maintain that HL minus HR less than or equal than 1. So we kind of in the best case, in your binary search tree which is balanced, you always have the heights of their subtrees are equal. Here is a little bit relaxation. We relax it by saying that for each node, the height of the left tree and the height of the right tree are different by 1, no more than 1. Okay, so the first, why the tree has the logarithmic height. That's probably the first. Like suppose that we did everything and the tree right now is in stable state and everything is under this condition, and we want to understand what is the height of the tree itself. You can prove that if the tree is of height h, then the number of elements is bigger than or equal than Fn, where f is the Fibonacci number. Why it is so? It is because, like, in this subtree you have bigger than equal than Fl, here then bigger than equal than HL, HR. And when you like add them, it is less than FH. If this is like, to be honest, like -1. Okay, so like we have here f-1 plus 1 is, sorry, we have to do vice versa, so it's bigger than fh1. Okay, so because this is in the, like, these guys are in the worst case fh-1 and fh-2, because they're like if you have height h, then one of the children are h-1 and the other one is at worst h-2. So this is exactly here. So one of them is h-1 and one of them is h-2. Then by adding this together, you can see that the number of elements in the tree of height h is Fibonacci number. And Fibonacci number is exponential. So it is approximately 1 plus that. Probably you know this from some course in mathematics in school. I'm pretty sure that you've done this, like solving the recurrency. So this is bigger than 1. So this means that the height of the tree is at least logarithm. If there are x values, then the height is logarithm 1 plus square root of 5x. This is the height of the tree. So okay, and you know that this is some constant times logarithmic x. You can turn you can withdraw this base of the logarithm by changing it to 2 or to 10, like this doesn't matter, and this is constant here out of that. Okay. Then the question is on how to restore the balance, how to make the rebalancing procedure. That's the question. Because like, let's remember how we did insertion in the binary search tree. We kind of go to the right, we go to the bottom and add an element somewhere here. What could happen? There could happen that some of the nodes, like all other nodes are fine except for the nodes on this path. Because for some of these nodes, their balancing condition is probably incorrect. Because we have height on one bigger suddenly. And so we should go upwards by this path and try to rebalance everything that comes to our glance. If we will see that there is imbalance, then we should rebalance it. How we will rebalance? So suppose we have, like, this is the first case. No, this is so what's happening with rebalancing? So we know that something like this happened. Please note that the unbalancing can be on at most 2 because we increase only by 1. So there can be that the height of the left is h minus 3 and the height on the right is h minus 1, and itself the tree is the height h. Okay. How does h, like there are several cases on how h minus 1 looks like. The first case is that h minus 1 looks like that. H minus 2 and h minus 2. I think so. Like if let me do this to be more precise. Let me draw them. I don't want to make a mistake here. Okay, I'm doing everything fine. So here is h minus 2, and what's happening is that we could, like this is the like this names the small rotation. So this is B here, A, h minus 3, h minus 2, h minus 2. So we just take all these five kind of parts of the tree and rebuild them in the different order. So we kind of take this B and we kind of traverse it here. So we take B as the root right now, and everything on the left is A, like this tree and this tree, and the right tree becomes here. So as you can see, here is the, like in this node the height is correct because it's h minus 3 and h minus 2. What is the height of this tree? Of A?
H minus 2. Because if we have h minus 3 below.
No. You have h minus 3 and h minus 2 below. Then what is the height of the tree?
No. So it should be h minus 1.
Yeah, it should be h minus 1 because we should take the maximum of these subtrees and increment by 1. Then this subtree is h minus 1, this h minus 2, and we're done. So we did a perfect rotation and everything is fine. So like this was easy because the heights of these trees were the same. Like suppose that one of them is h minus 3. So the height of this guy is h minus 1, as we remember. And there are two options, like either this h minus 3, this h minus 2, or vice versa. Suppose like that. Then let us write what h minus 2 is. H minus 2 is some node h minus 2 here, and it has two children. One of them is h minus 3, and another of them h minus 4, h minus 3. This guy is h minus 2, then one child should be h minus 3, and the other we don't know exactly. Okay, and for that there is a big rotation. We have 3 nodes here, so let us put these 3 nodes on top. So we will have C, A, B, because like if you see B is bigger than A, and C is less than B and higher than A. And then we have these subtrees, and we will put them in their order by giving A here, h minus 3, here, h minus 3, here, h minus 3, h minus 4, here, h minus 3. So what is, you can see that this node is balanced because both of its children are h minus 3. So can you tell me the height of A then?
H minus 2.
In h minus 2, okay. So on the right side there is h minus 2 and something like either h minus 3 or h minus 4. Then the height of B?
In the worst case it would be h minus 3.
How it can be h minus 3?
When this, the left one is h minus 4.
You are doing the same mistake again.
Oh. Well, actually, if one is h minus 3 and...
Yeah, if one of them is h minus 3, then the upper one should be h minus 2.
Yes.
There is no way to change.
Yes.
So here is h minus 2, and then the parent?
H minus 1.
Yeah, h minus 1. Okay, and you can see that these guys are balanced also. So this is h minus 2 and h minus 2. They're balanced, and everything is fine. So we have like this bunch of rotations. So like there are like this is RL rotation. There is of course RR rotation. Is that when this guy is bigger, like this guy is h minus 2 and this guy is h minus 3, then you should open this subtree into like this and then put them again in the right position, like like next time it will be like if we consider this, here is h minus 3 and here h minus 2. Then you will have A, B, C in the order of like smallest to the largest. Then you will have A, B, C here and the same trees like and in this position, like the same position. So this goes here, this goes here, this goes here, and this goes here. So as you can see, unfortunately this is a little bit complicated, right? So to to write because there are several rotations and it's pretty hard to do them correctly and it takes a lot of time to write, but it's logarithmic at least. So we know how to do their perfectly balanced tree and there is no randomization and nothing else. Like there is, for example, red-black tree that works, that has 8 different rotations. Like it is even more complicated. There is splay tree that has zigzags and zigzags. But this is one of the simplest deterministic binary search trees that are balanced. Okay. So this is, I'm just only giving you as I do not ask you to write that, but the next tree I would like to ask you to write in the whole works to implement them all there. To implement them. So like, this is Treap. Treap is kind of the merge of two things. It is tree and it is heap. What does it mean? So suppose that each node, like previously, each node contained only one value, which is key, that we are storing there. Now let us suppose that we store priority there also, which will be random. And we build a tree. So we have, it will be key and priority, which is random for each node. We will generate randomly. This means that this tree will be the correct binary search tree by the key, but by the priority it will be heap. So suppose that 1, 2, 3, 4, 5, 6, and their priorities are, I don't know, like their topmost priority will be the smallest one as in the heap. So this is 1, 2, 4, 7, I don't know, 3, 4. Something like that. So like by their key, this is the binary search tree, so this is 1, 2, 3, 4, 5, oh, sorry. This is less. It's less, so this is 5. And by their priority, this is heap. So this is 1, 1 is less than 2 and 4, 4 is less than 4 and 3, and 4 is less than 7. There is only one way to build, if all your priorities are different, there is only one way to build a Treap out of that. Why so? Why do you think? Why do you think it is the only way? So suppose you are given kind of key 1, like in the sorted order, key 1 priority 1, key 2 priority 2, and kn priority n, and you know that k1 less than equal than kn. And you know that all the priorities are different. Why there is only one way to build a tree? Or can you come up with the algorithm, like which is not necessarily to be linear, how to build the Treap out of these nodes?
Well, as first, I think we should find the minimum priority.
Okay. And where it should be?
It would be the head.
Yeah, it would be the root. Okay, great. So we find the km, pm, which is somewhere here. Then how to build the rest of the tree?
By the keys, I guess.
What are you doing next? So you find there with minimal key and makes it the root. So it was somewhere here. How to build the rest of the tree?
We found with minimum priority.
Yeah, we found the minimum priority. Yeah. Yeah, it's indeed the root because like it should be heaped by priority, so like it should be in the root. There is no way to do that.
Yeah, well, maybe we could find divide the rest of the elements by those whose keys are less, whose keys are greater, and then find the minimum of them and do it recursively.
Yeah, exactly. So it's just you have the split point, and you have the rebuild tree out of left and rebuild tree out of the right, and set this as the left and the right child. Yeah, as you can see, this building procedure is not random, and there is only one way to build it if the priorities are all different. Okay, that's an interesting insight, but like this doesn't appear to be logarithmic. Nowhere. Like it still can be that. It can be k1 1, k2 2, kn n, and you have no way on how to put them together. You just say it's in the root, then the right child will be this one, and etc. And you will have kind of the height of the tree is linear. Understand?
The last thought was wrong.
What?
The height of the tree would be linear.
Yeah, fine. Like because well, if you take
the height would be linear.
Yeah, the height will be linear.
If it's exactly such case.
Yeah. If it's exactly such case, so it will be linear. So this is not what we want really. So for that, it is specifically you can like to resolve this issue, we will generate the priorities randomly. And when you generate them randomly, their expected height of the tree is logarithmic n, or of logarithm n. It is not trivial to prove, but it is pretty easy to state.
Yeah, it's intuitive.
Yeah, kind of you take the middle element because it's random priority, so like you kind of take some element in some reasonable with probability 1/3, like this is exactly what we did with quicksort, kind of, right? So we know with the probability 1/3, we will take an element that is in the middle and kind of split it into parts, which are of h-3 or 2h-3, and then like kind of you can build them. So this is exactly as this is kind of the same as quicksort algorithm. Okay. Okay, so we know how to build a Treap when you are given the keys and priorities. However, it is not so easy to write. Not so like we have to do this faster than taking the minimum out of it, and while we have it to be dynamic, so we have to insert and remove elements like in the real time. So we have to do something more creative rather than that. For that, the tree provides two operations. There is a split operation that takes tree and x and return like the tree that contains everything less than x and tree that has bigger than x. So like it returns pair. And there is a merge that takes two trees, 1 and 2, where like the left one, like let it be left and right, the left one, the keys on the left are all less than equal than the keys on the right. So this is very important. So you can merge on the trees that Like that's kind like each tree supports, each tree is itself some segment. So you can merge kind of two segments that are not, that do not intersect. And you can merge them together and you will get one tree out of them. So the first question is that, for example, I want to do insert X. How could I, using split and merge, do insert procedure? Yeah, of course we will create, like, let it be, so there will be a node X, which is new node at X and some random.gen.
Well, we should split the tree by the X and then add it to one of the trees.
So we kind of do split by X, and then, like, this is left, this is right. Then what you are doing?
Then we should add the X to one of the trees.
How we can do that? We have two operations. We have split and we have merge. Like this one is this is kind of the tree of one node only.
Okay, yes, we can merge this tree of one node X.
To whom?
I think it should be the left tree.
Okay, so we take the left tree equals to merge left tree and X, and then what you are doing?
And then merge it with the right tree. Okay,
great. And then return merge L R. Okay, so what you have done, you just split by everything that is less than X, then you add X in the middle, and you merge with everything on the right, and the merge is still correct because, like, you kind of merge everything that was less with everything that was bigger. Okay, so this is insert. How to remove X? It is a little bit complicated, just a little.
Well, I guess we should split by X at first, also.
Okay, we split by X. Okay, that's the good start. So we have split by X. So this guy is less than X, and this guy is bigger than equal than X. Okay, what we should do next? Suppose we store integers.
Well, maybe we should split the right one, which contains X, with the X plus 1.
Yeah, exactly. So, like, we will get some. So if you split by X plus 1, you will have here everything that is less than X plus 1. So if you use this, then here will be X, and here everything that is bigger than X plus 1. Then what we should return?
The merged first left tree, well, first and fourth.
Yeah, exactly. So kind of what we have done here is that we kind of split this into two parts where this X, like, retrieve the X and merge them together. Okay, great. So we almost know how to do the split and merge. Oh, insert and remove. Now we will be talking about how to do split and merge on its own. Like I will be writing in kind of pseudocode. So try to understand, like it will be a little bit different in your language of choice when solving this problem. So, okay, so we want to do split. It will be n and x, where x is the node. So, if n is equal to null, if it is an empty tree, we should return the pair. What should be in the pair? So we have pair. So if you split empty tree into two trees, what they will be? Two empty trees, yeah. So you return null here. Okay, great. Then you have a tree. So you have here n.x, so this is the middle. So, and you want to split by x. If x is bigger than endpoint x, if n.x less than x. Oh, let it be not x, let it be key.
I'm sorry, what does it mean n dot key?
Yeah, so n is the tree. Mm-hmm. So this is a node, and we compare the top. So this is kind of like, this is typically implemented as the class node. So there are key, priority, node left, and node right. So kind of like this is their key. You store the key in priority, and you store left and right child.
Oh, so n is the topmost.
N is the topmost, yeah. So you kind of store somewhere the root of the whole tree, and when you need, you just pass this split n to x. So if n key is less than x, what you could say about this?
Well, that it's also less than x.
Yeah, it's also less, and it should go to the left tree in the answer. So we could split this tree by x here, like recursively. We could split it by x. Then, can you tell me, like suppose you split by x and you return them like that. So this is the situation. So you kind of split the right child by 2 by x. It returns 2 trees. And you want to return 2 trees also further up. So how to make 2 trees out of them?
Well, can we use merge or?
No, there is no need for merge. Like the right, there is no right child here. So we could do like that. We could connect the right child to this guy. So we can see, so we take left, right, split n dot r by x, and we say n dot l equals to n dot l equals to, oh sorry, n dot right equals to left, and we return n and r. So this is exactly, we split it by left and right, we set the right guy to L, and we return the pair as n and r. So what we do else?
Well, we should do the opposite operation.
Yeah, how to do that?
Yes, we could do the split again, but split to left.
Okay, so we got LR split and left by X. That's what we're doing.
And then we should assign the end of left. Well, we should assign R to the end of left.
R. Okay, and return. What to return?
And left.
L and R.
Yes.
L and L. So this is the whole split. There is nothing very hard about that. You just correctly split them. Okay, so I will need this further. So let us write merge. Merge L and R. So if L is null, like when you merge empty tree with R, what you will get?
We should return R.
Yeah, we could return R. If R is equal to null, then what we should return? Then we can return left. And then finally we should merge. No. Okay, so we have two trees, left and right. Can you tell me which one will be in the root of the new tree?
The right one should be in the root.
Who is in the tree?
Hmm?
Who is the root in the tree?
I guess the right root, but
Why? Why right? So each node contains key and priority. Like why the right should be in the root?
well, I guess in root should be the one with the minimum priority.
Yeah, exactly.
Yes.
Exactly. So like you know that the root should be the minimum priority. You know that this guy is the minimum in this subtree and this guy is the minimum in this subtree. So like one of them should be at the root and the left, like which one is less than it should be. So if left dot priority less than R dot priority, then what we should do? So like that's. So suppose that left dot priority is less than dot right. Okay, so what's happening with the left tree in general? It remains the same.
Well, yes.
Yeah, okay, and what's happening with this two? Like there is, like this is the root, like this is the current, our root, and what we should do with these two trees?
I'm sorry, I missed the left. The left one.
So this is the left.
Tree.
Okay, we know that this guy is the root. Okay, so everything here is less than or equal than that. So like you know that the left child will never change and it's fine.
Yes.
While the right child should contain something out of these nodes. What it should be?
Well, I think we should suspend it somewhere in the.
Okay, probably it's too complicated question. We can merge them.
Hmm?
We can merge them.
Oh yes. Okay.
Yeah, we can take this root separately. We merge these trees together and put back as right child. So you just say here L.R equals merge L.R and R. And what's in the next case or in other case?
Well, we should again do the same thing, but for the
Mhm.
R.L merge R.L and left and
Not exactly. Yeah, you're right that we have to merge right left and the left. But it's very important in what order. Because you can merge only if the left is less than the right. So what order should be?
Yeah, I think that left L should be the first.
Left L. Okay, so let me draw this. So we have left here. Then we have right, which is right.left and right.r. So again, right.r is fine, and we want to set right.left. Home we should merge. We should merge. Yeah, indeed. R.L and L. But in what order? You should merge.
Oh, yes.
You should merge L and then R.L. L because they're like L is less than R.L. Okay. That's it. So we have insertion, we have split, we have split and merge, and then we have insertion, deletion, and like contains is trivial because you just go to the corresponding part of the tree where which is less than x or which is x. So like that shouldn't be the problem. Okay, now let's support a little bit more complicated operations. So suppose that we want to know their sum of the subtree, like the number of nodes in the subtree. So we contain here count. So why we need that? Because suppose we split the tree into some parts. So you split like that. For example, you want to count the number of elements that are bigger than x and less than y. You just split by x here. You just split by y here, and take the count of this subtree. What should we do to support that? Again, let's see what's happening here. So we split recursively n.r by x, and we get left and right. Suppose that we correctly calculated the counts of left and right. We will maintain the invariant that every time we call split, everything that is returned already correct. So each node has their real number of count in the root. So we this count is only maintained the number of elements in its subtree. Okay, so L and R are the same. So can you tell me which node has the incorrect number of incurrent count? We know that n.count here was correct, but you can see that here it wouldn't be correct because you just changed the child.
Yes.
So you have to intern a special operation which is named recalc n. And how recalc is performed, so we say n.count equals to n.l.count plus n.r.count plus 1. So we just know that we changed n here. We know that n has changed, so and its subtree is already correct. So to recalculate, we just know that the count of the number of elements in this subtree is on the left, the number of elements on the right, plus 1, because this is the topmost, one element that we didn't count before. Please note that if n.l is equal to null, you will have here null pointer exception, something like that. Please be careful here. So it should be this should be either with if or ternary operations, but for simplicity I will not write it here, but like it is implicit that there can be null. So and you place it here. Okay, so we know recalc m. So what's happening here? Oh, sorry, I forget we should return something. Return L, else r.l equals to merge L r.l to R. Okay, how to fix merge right now?
Well, again, after changing the child, we should do the recalc.
Okay, so here recalc whom?
Recalc L.
Recalc L. And here recalc R. Okay, great. Okay, that's good. So now we know how to count the number of elements in the subtree. And suppose we had insert, remove, we have contains, and suppose right now we have an operation kth. So that returns the kth element in our set. How to implement it? So we want to find kth element that is past k. You know that we already have counts, so we already calculated the number of, we can maintain the number of elements in the subtree. That's already not the problem for us.
So we start from the root, and then we check maybe it's the left count, if it's less.
Oh, sorry, there is a node n, of course. If n.left.count is what?
If it is greater than k, then we should go to the left row.
Greater than k, then what we should return?
We should do the same case operation with the
kth. What we should call kth recursively?
Yeah, I think it should be, well, obviously n.l and k also. Yeah.
Okay, good. So what other condition?
In the other case, we should go to the right subtree, because
Not exactly.
If it is equal, then this element will be the case.
Return. No, you know that there should be like k minus 1 to be more precise. Bigger than equal to k. Like if the number of counts is k minus 1 on the left, then
Yes.
this guy will be the kth. And the other one, otherwise, what we should return?
Well, yes. In other case, we should go to the well, we should check the right subtree, I guess.
Okay, we check. So from which we should call kith. So we just do this recursively, like as contains.
I guess the only left option is n.r.
N.r. Okay, and what is there like? What's the value should be?
So if we have k elements in the subtree, yeah, I think we should subtract the size of the left tree from the k. Is that right?
What we should subtract the left subtree.
We should subtract, yes, the count in the left subtree.
So it should be what? K minus?
K minus n.l dot count.
Not exactly.
Maybe minus 1 somewhere.
Yeah, minus 1 because like the root of the tree is itself should be counted there. Okay. So suppose like a little bit like again question. So suppose that instead of count, so we had an operation count that counts the number of elements that are bigger than or equal than x and less than y. Okay, and right now we change it to calculate the sum of the elements that are there. What we should do, if we want to calculate the sum of their elements that are bigger than k and less than y.
Well, I think we should store the sum as well as we store it. Well, the same way as we stored the count.
Okay, and how we should update it?
Well, we should also recalculate it. Maybe we could do the same operation.
Okay, how to recalculate this, guys? N.sum. How to recalculate N.sum?
It should be n.l dot sum.
N.l dot sum.
n.r dot sum.
R dot sum.
Plus the key of this.
N dot key.
N dot key, yes.
Okay, great. Okay, to be honest, I think this is it for today because like then like I think it's not very clear from the first time, and like I don't want to get like the next time we'll go deeper into that, but like right now
into the Treap.
What?
Into the
into the Treap, yeah. It will be a little bit like. Okay, let us probably try, like, I will try to explain something next, and if it will not go, like, we will stop and, like,
okay.
we will. So, suppose right now we have we know that we have elements in our tree that are from 1 to n. Like just from 1 to n. So like you have 1, 2, 3, 4, 5, 6, etc. And so like your tree is quite clear, and like you can understand, like kind of we will model in this case we will model another data structure So we have an array A, and we want to do several operations on it. So we want to do two operations. We want to add from L to R, add LRX, and for example, calculate their value C. Value P. So what does it mean, value P? Value P, this means that it returns the pth cell of A. Okay. Now it becomes a little bit more complicated than usual because we need to update. Okay, let's probably not value of P, like it doesn't matter. So it will be the sum of elements from L to R also. Like we have two operations, add some element on there, like from left to right on by X, and to sum all the elements from L to R. Like for that, we will maintain the tree with corresponding, like so this node will be the node with key 1 and some priority. This guy will be key equals to 2 with some priority, and etc. And we build the tree out of them. Right now, what? So how to, suppose we do not have add, right? And we want to only count the elements, like the sum of the elements from left to right. Oh yeah, so, and you have like here A1, A2. So how like if we forget right now about add and we have only sum, it's easy to recalculate because we just simply call here recalc, where n sum will be not n.key but n.value. Let us store it there. So this guy is value 1. Sorry, value here is, this is also value, and etc. So kind of it is exactly the same. If you forget about add operation for now, and to answer only sum on the subtree, this is exactly what we want. You just split by L, you just split by L, you just split by R, and take the sum in the root. How to deal with add right now? Add will be a little bit more complicated. For that, we will do lazy update. So kinda, so we split by L and R and have so like in our node we will have, except for a count, sum, we will now store the add. So when we split, so here is from left to right, and we have it the root. So let us say that we set this dot added plus equals to x. So we kind of say we will add to this string, to each of its element x, and kind of stop there. So this is the whole add procedure will be. So the split and add here. But something will a little bit change, because when you split to n, you could have at n some lazy operations that are waiting there. kind of that we put in back like in the past, but we haven't propagated. So kind of we say here, so it is add plus equals to x, so everything here should be incremented by n.add. So, and we kind of, what we want to do, we want, when we get to the node, we will do the following. We will propagate this operation slower, kind of. So if, like, suppose that we come to that node and we know n.add here. So what we're doing, we say, okay, please add to these guys n.add. So we kind of put them, like, please, like, you know that you have to increment everything here by n.add. And we increment the value itself by add, because like we kind of propagated it and we have to change to the real value. So value plus equal n.add. But something also changes a little bit. For example, when you calculate sum, you will get to the position that, again, okay, no, not like that. So when you push down, how the sum changes in the subtree?
What do you mean push down?
Yeah, we take n.add and push them to the children. Kind of, we have to increment all the nodes in this subtree by n.add. So we set n.add to 0, so there is nothing changing. But we should increment the value in this node by n.add and say to its child, please we have to add to their subtrees.
Okay, do we do it right now or in a lazy manner?
Yeah, we're already doing it in lazy manner. So like we do not recurse further, we just pushed only once.
Okay.
So how n.sum will change?
It will be plus 2.
Sum is the total number of values in the string.
Well, then it should be count.
Okay, it should be count, good.
Count multiplied by the n.add.
Yeah, exactly. So this is kind of our new push operation. It is going to be push with node. So we say that n.left.add plus equals n.add. n.right.add plus equals n.add. Then we say that n.sum plus equal n.count times n.add. And finally n.add equals to 0. So nothing changes here. And now we should place it everywhere in our split purge operations. So you kind of, each time you visit a node, you should push it. You just, when you visit the node, you just, here you should write push n. The same here, you just have push left, push right. So kind of, the root is always without, like when you push it, the root is always without these updates. The only issue is that when you take sum, you will be returned some tree with probably add at the top. So you have to return not only sum, but like this. Or when you do like some left right, you like split 1, split 2, then you have node, then you take n node push n, and then return n dot sum. So you do not have to forget to push it here. Or if you want to be 100% sure, you should push here, like push n.l, push n.right, like here, in both here, like to push everything here. But it definitely should be pushed later, because you do a recursion, and if you go to the n.left, then you should push it here.
So basically, every time we do a recursion, we add pushes there.
Yeah. Yeah, exactly. Exactly. Okay. It's about time. Yeah, I think right now, like, I will stop here, like, let it be a little bit. I know this is a little bit complicated with this global